Hi, everyone. So this is me again. And the paper of the authors of this paper, due to the travel restrictions in China, they cannot make it. So I will be the proxy to present their paper on their behalf. And what they want me to do is a little bit different. So they would like me to give a very short introduction of their paper. Then after that, they prefer to play a video presentation that is pre-recorded. So I will spend a few minutes to describe to you what this paper is basically about, then I'll play the video. All right. So this paper is targeting on IoT environments, and you can see wireless communication is heavily needed in most of the IoT applications, because if you are having a large amount of sensors and actuators, you really need to wirelessly transmit data between these small devices and the sink or the base station for different purposes. And there are different ways of doing wireless communication in IoT. And most of the existing devices that we're using currently, they are doing active communication, in which they use battery-powered devices to use commodity Wi-Fi networks, Zigbee networks, Bluetooth networks for the transmission. But the major problem is that they are battery-powered, so they are expensive, and in many cases, they are not suitable for many embedded and power-constrained IoT applications. So instead, the authors claim that backscatter is going to be a better choice, and we have also learned this from the previous papers. So basically, the backscatter devices are passively powered by the ambient signals, so they don't need to be powered by batteries. So with that being said, they can be made very small, they can be consuming extremely small amount of power, and they have a better fitness to larger variety of IoT applications. And within this paper, the author's major contribution is that they are developing a new backscatter system called Content-Agnostic Backscatter. And the uniqueness of this approach is that when they are trying to do backscattering, they do not require any knowledge about what they call ambient contents. And you will see the more detailed definition and formulation descriptions of such ambient contents in their video presentation. And at the same time, although they do not require such prior knowledge, but their system can still achieve the similar level or even higher level performance when being compared to the existing backscatter system. So I will stop here, and please play the video. Yeah, I believe there are audios. I tested it at my side, but all right, okay, thanks.
Does anybody have any good jokes?
Content-agnostic backscatter from thin air. Wireless connections are ubiquitous and scalable, which makes them popular in IoT applications such as smart homes. Basically, there are two kinds of wireless communication in the IoT. Active communication generates wireless signals with the power supply. It is not very friendly for IoT nodes, since expensive hardware for active radio is a burden for low-cost devices. And on the other hand, huge power consumption is another problem, since power outages make communication unreliable, and changing batteries is a labor-intensive task. The backscatter system tackles these issues by passively reflecting ambient wireless signals. Compared to active communication, it is cheaper and consumes much less power. Thus, backscatter communication is friendly for low-cost IoT nodes. To decode chat data, recent systems need ambient content for reference. They either use an auxiliary receiver to get the ambient content, or use signals from a helper transmitter that sends predefined content. Then they demodulate the chat data with the help of ambient content. Working only with content-aware situations is a barrier to their use in IoT applications. We ask a simple yet difficult question. Can we enable backscatter communication in a content-agnostic way? Our key insight here is to create a virtual single tone at the center of OFDM symbols, and the backscatter tag treats ambient signals as single tones. We use phase-shift keying to modulate the virtual single tones. In this paper, we present CAP, a content-agnostic backscatter. While recent ambient backscatter systems have to use reference, our system demodulates chat data from the zero subcarriers and the ambient data from the data subcarriers. To achieve our goal, we face three key challenges. First, how to demodulate chat data. Second, how to demodulate ambient data. Furthermore, we find that OFDM backscatter systems need subsymbol level synchronization. How to achieve it on text is also a challenge. Now let's see the first challenge, how to demodulate chat data. This is the signal transmission process of our system. The phase of subcarrier J from the received symbol I can be indicated by this equation, which takes into account ambient modulation, tag modulation, wireless channel, and RF front-end arrows such as STO, SFO, and CFO. For zero subcarriers, J is 0. We focus on equation 1. Next, we show how to extract the phase of the chat data. We find that zero subcarriers have several advantages. First, according to the standard Wi-Fi, no ambient data transmits on zero subcarriers. The phase of ambient data is 0. Moreover, we find that STO and SFO do not affect the zero subcarriers. Therefore, the phase of the STO and SFO are 0. In addition, after channel estimation and CFO calibrations in standard Wi-Fi, phase of the channel and the CFO become common phase error or CPE. Thanks to these advantages, we have significantly simplified the equation. The zero subcarrier phase is equal to the CPE plus tag phase as equation 2 presents. To solve the tag phase, we first estimate the phase of zero subcarrier, then remove the CPE. To estimate the phase of the zero subcarrier of the received symbol, we can simply average all of the pilot subcarriers and calculate its angle. However, we find the cancellation points using simple averaging are too dispersed, leading to low accuracy. Then, we propose a weighted least square phase estimation and perform it for all symbols. We can see that through weighted least square estimation, the cancellation points are gathered around a circle since it still contains CPE. Our next step is to remove CPE. We have two key observations about CPE. First, we find that CPE keeps accumulating across symbols in a packet due to the residual SFO. And secondly, the CPE of the first symbol is near 0. Based on our observations, we propose an iterative CPE separation scheme. Initially, we assign 0 to the CP estimate of the first symbol. For each symbol, we assign the CP estimate from the previous symbol to that of the current symbol. Then, we estimate the tag phase according to equation 2 we deduced before. As the pictures on the right depict, the red sector is the CPE we estimate from the previous symbol, and the green sector is the phase of zero subcarrier, which is estimated by our weighted least square scheme. The yellow sector is the tag phase, which equals to the phase of zero subcarrier minus CPE. Next, we update the tag phase to the phase of its closest consolidation center. The blue sector is the closest to our yellow sector, so it becomes our new tag phase, and we get the tag data of this symbol. Then, we update CPE using the new tag phase estimate and equation 2. We update the red sector using the green and blue ones. This iteration is completed and we move to the next symbol. We successfully remove the accumulating CPE through the above iterations on each symbol. However, we notice that there are some stragglers in the consolidation diagram. We find that those are simple assembly errors caused by STO. In the regular case, the receiver assembles a certain number of sampled points into an OFDM symbol. However, due to the STO, the sample points might be lost or redundant over time. In this situation, we choose to either duplicate or drop some points according to the STO we estimated. Results show that our operation makes the consolidation points into perfect PSK clusters. We can get the tag data by demapping these points to the closest consolidation centers. Now it comes to the second challenge, how to demodulate ambient data. The backscatter OFDM symbols experience different channel conditions due to tag modulation. We noticed that the phase tracking, which is operated over symbols, works badly when demodulating ambient data from backscatter signals. Thus, we propose a customized phase tracking scheme. We first subtract the zero subcarrier phase, which contains tag phase and CPE. Then use standard Wi-Fi phase tracking and demodulation to successfully recover all the ambient data. Now let's see the last challenge, how to achieve subsymbol synchronization. Our system requires that the tag accurately synchronize with the ambient signals and perform modulation on OFDM symbols. If the tag modulation drifted due to delay or other reasons, the modulation will be invalid because the failure of FFT incurs error in our zero subcarrier estimation and ambient data demodulation. Therefore, we need subsymbol level synchronization. We designed a timing synchronization scheme that uses the receiver's feedback. First, our tag detects and synchronizes with the ambient signal. It determines a call start and implements an interval search. Then the tag backscatters the signal and waits for the response from the receiver. Upon receiving backscatter packet, the receiver demodulates ambient data and sends a response about whether the tag takes the optimal synchronization point. In the end, the tag receives feedback from the receiver. In order for the low-power tag to decode data from the receiver, we transform OFDM signals into ASK-like signals, which can be decoded by an envelope detector. We built 3 type prototypes. The first one is for verification. The second one is for battery-free application. Furthermore, we also present an ultra-low power IC simulated prototype. The power consumption is shown in the table. The total power of the battery-free prototype is 8.45 milliwatt, which is 2.75% of the verification prototype. And the IC simulated prototype can further achieve a power of less than 300 microwatts. Now let's see the evaluation. For our receiver prototype, we use the ZBoard ZYNQ7000 and the AD-FMCOM S3. It supports 2x2 MIMO, 40 MHz bands. For ambient excitation, we comprehensively use all kinds of OFDM Wi-Fi, including Wi-Fi 3, 4, 5, and 6. Furthermore, we also consider different MCS, length of GI, channel bandwidth, number of streams in OFDM Wi-Fi. Since advanced Wi-Fi enables multi-user, we also test it in our evaluation. This is a comprehensive end-to-end evaluation of our system. In this table, we can see that CAB works smoothly with all kinds of OFDM Wi-Fi we mentioned before. Besides, both tag data and ambient data are successfully demodulated in our system. We compare CAB against FS Backscatter, FreeRider, and MobiSys. Results show that our system outperforms in terms of tag and ambient throughput. When the tag RX distance is 0.5 meters, CAB achieves around 1097 kbps tag throughput and around 139 Mbps ambient throughput. Next, we show how CAB leverages uncontrolled ambient traffic for application. We let a Dell laptop connect to an AP and generate normal Wi-Fi traffic by downloading a file and playing an online movie. Our battery-free prototype takes this traffic and backscatter image data from a camera. Results show that CAB enables battery-free live stream with ambient Wi-Fi traffic. The text stream traffic is similar to the excitation traffic.
All right, thanks for the time.